Hello. In this session, we are going to discuss Chinese remainder theorem. It's an interesting concept of the remainder theorems. Now, becomes a little difficult also for some students because this is not something that we have been taught in our school days. So the theory becomes a little challenging to grasp in the first stage. This is a little algorithmic, so please pay attention to what I am saying. Also, there is a special type of questions that becomes very easy to solve with the Chinese remainder theorem. There are other remainder theorems also, but this is one of those things. This is not very much important for CAT, but very relevant for your aptitude development if you're into, let's say, increasing your aptitude as a whole. So the typical question type that you will be asked in such question types would be a recurring number. So a number that is given to you 131313 something. I'm just taking a random number. Let's say up to 300 digits, and they are specifically asking you to find the remainder when this thing is divided by a divisor, let's say 99. So what is the remainder in this case, right? So how do we solve this thing? So we'll understand that thing. Again, let me just remind you that because this is a little bit algorithmic, so you'll have to remember certain things in order to apply the ideas very effectively. Now, obviously, the usual division process will be very painstaking because the number is humongously big, 1313, 300 digits and so on and so forth. So dividing by 99 would become much difficult. Now, what if I tell you that instead of this 300 digit long number, you have been given a number which is, let's say, just 2-3 digits long. For example, a number like 100 divided by 99 or 150 divided by 99 would have been much more easier for me to calculate than this humongously big number. So the idea of Chinese remainder theorem is that we are trying to reduce this number to some manageable number, and that reduction business is done through a process of arithmetic progressions. So we are in the lookout for finding an arithmetic progressive series of numbers a, b, c, d, e, ... and after, let's say, a considerable length, you will find this number n also in that arithmetic progressive series. Now the concept of Chinese remainder theorem says that the moment you find this series, obviously because it's an arithmetic progression, you will also know the common difference. And the concept says that any one of the terms, let's say we take a term d, or just for the sake of simplicity we take a, by the common difference d, this remainder is going to be exactly equal to the number n divided by the common difference d. So either it is a dividing by the common difference or a factor of the common difference, but you will realize in our case the common difference is going to be 99 itself, which is the divisor, right? So now let's start making sense of the question. The very first thing, the divisor is a composite number, right? So we have 131313 ... let's say 131313, and this one is my 300th digit. This thing when gets divided by 99. 99 is a composite, as I have mentioned right now. So what you are supposed to do is that break it into co-primes, because in that way it would have been much more easier for me to predict the remainders, right? In one way, I am trying to use Euclid's division lemma, which is dividend is equal to divisor into quotient plus remainder. Okay. Now, using this Euclid's division lemma, I am going to find out the value of the arithmetic progressions, right? So this is 9 and 11. You can see these are co-primes because the highest common factor between them is 1. HCF is 1, right? So the first question that is now I'm going to ask you is that what is going to be the remainder when this number n is divided by 9, and what is going to be the remainder when the exact same number is going to be divided by 11. In both the cases, you will realize you will find a similar equation, n is equal to dq plus r, or you will get, let's say, ap plus, let's say, r dash, something like that. Because both of them are equal to n, we can equate them, and by equating these two equations we will get an arithmetic progressive series. Let's see how we do that. Okay, so I'll just take you to the clean space, and now let me proceed, right? So 131313 ... till 300 digits. The first job that I have is that I need to predict the remainder when I divide this thing with 9. Now the divisibility, let's revise the divisibility rule of 9. The divisibility rule of 9 says that any number, if it is divisible by 9, the digital sum of the number should also be let's say multiple of 9, or should be 9 itself, right? So as you can see, the number itself is of the form 1 3 1 3 1 3 dot 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 1 3 1 3 and 1 3. Again, I'm saying that let's suppose that this 3 is the 300th digit. Now you will see a very peculiar pattern in this. From the right hand side, if I club these two digits, because I need to find the digital sum, and I see the two digits to be similar, and then this group itself let's say repeats. Okay, so what is the sum of this 1 and 3? Obviously that is 4. And how many groups of two digits I will find? I'm pretty sure you may have understood it, because in all there are 300 digit single digits. So if I take two digits ka pair at a time, there will be 150 digits. So the obvious summation of this thing would be, when I do the remainder, obviously please remember we are reducing the numbers, right? It is going to be 4 into 150 upon 9, the same thing. We are doing the remainder business. Now this is as good as 600 by 9. Now at this point you can divide this using your any method that is suitable to you. I would say still, you know, do the same thing. You know, just see 0 plus 6, that gives me a 6 itself. So it is going to be 6 upon 9. Now the divisor is more than the dividend, so the remainder in this case is going to be nothing but a 6 only. In other words, if I am allowed to write the number n in the Euclid's division lemma format, when you divide this thing with 9, you get some remainder, let's say some quotient, say a, and the remainder 6. This is my equation number 1. Now remember, this equation number 1 and equation number 2 that we will get after dividing it with 12, finding the remainder, will help us finding that arithmetic progressive series. Now let me divide the same number with 11. It's a little bit of a laborious task, so you will have to keep on remembering the ideas also simultaneously. So 1 3 1 3 1 3 dot 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 1 3 1 3 1 3. Now there are several ideas to find out what is the remainder when you divide this thing by 11. Please recall, the divisibility rule of 11 says that you will, from the right hand side, always remember, from the right hand side you will always make group of alternate digits. You'll add them. Okay, so 3 plus 3 plus 3, and the difference of the digits alternately from the tens place, or the tens digits place. Okay, so it is going to be 3 plus 3 plus 3. How many times? Yes, 150 times, because single digit, total number of digit is 300. So single digit, it is going to be 150 minus 1 plus 1 plus 1. How many times? It is going to be 1 into 150 times. Now 150 you can take out as common, and 3 minus 1, that is 2. That is 300. Now remember, this thing is still more than the divisor 11, so we can still further do our business. Now at this point it is not very difficult to calculate the remainder, but I would still say stick to the method that we have used. So 0 plus 3 minus 0, that is 3 upon 11. So the final remainder in this case comes out to be 3 itself. Okay, this is the final remainder when we divide the number n with 11. So my number with the Euclid's division format, I can write it like n is equals to 11b plus 3. This is my second equation. Now I will quickly show you what we have got as the first equation, that is, let's say 9a plus 6, and the other one is 11b plus 3. Now because n is equal in both the cases, I can do this thing. N is equals to 9a plus 6, that is equals to 11b plus 3. Now see what I can do from there. 9a plus 6, this 11b can be written as 9b plus 3b, because 2b plus 3. Okay, so 9a plus 2b is equals to this thing. Now if I take the 9b to the LHS, I get 9a minus 9b, that is equals to, taking the 6 to the RHS, it becomes 2b minus 6. If I take 9 common, this will become a minus b, that is equals to 2b minus 6, and at this point this you can very well write at 9x is equals to 2b minus 6. Now at this point it's all but hit and trial. You'll have to substitute some values to find out the exact let's say value for a, b and c. So which first number that you substitute actually satisfies this equation? So if I substitute b is equals to, sorry, this is 6 minus 3, that is minus 3. Okay, extremely sorry for that. So if you realize that if I substitute b as 1, this becomes 2 minus 3, does not satisfy, and I'll not get a 9. Basically what I'm trying to say, I just need to find out a 9 when I substitute randomly for values of, so till 5 you see 10 minus 3 is 7, not equal, but the moment I substitute b is equals to 6, I get this 6 into 2, that is 12 minus 3, that is 9. So b is equals to 6 actually satisfies this equation. That means for a for a similar value of b, I can find out the value of my n also, which is going to be what? Please look at this part. 66 plus 3, the value of n comes out to be 69. Okay, remember we were finding the arithmetic progressive series. This is the first term of that series. Okay, and similarly I can find out a value for a also. If you realize, this is going to be, this part is going to be 69, and 9a plus 6 is equal to 69, 9a is equals to 63, a equals to 63 by 9, that is 7. Now hold on. So what is my number finally? At this point, my dear friends, the number itself will be 6, 7 and 69. Now the arithmetic progressive series is going to be this only, and please remember the next number, the next digit for b, the next digit for 7 and the next digit for 9 will be, for b it is going to be in the steps of a. Remember the equation that we have, 9a plus 6, this is one of the equations, and the other equation is 11b plus 3. So the next digit for b is going to be in the steps of the coefficient of a, that is going to be 6 plus 9, that is 15, and so on and so forth. Okay, similarly the next digit for a will be in the steps of the coefficients of b, which is going to be what? 7 plus 11, that is 18, and so on and so forth. And what is going to be the next digit for the, let's say this n, the term n, the second term is going to be nothing but a common difference is 99. Remember the divisor itself. So 69 plus 99. So 69 plus 99, we can do this orally also, but just for the sake of clarity I'm doing it over the 9 9s are 18. This is 17 plus 1, 18, right? Hold on, this is 15 plus 1, 16, so 168. Okay, I mean you can have many more terms, and eventually after a again considerable length you will get the number n, which is 131313 dot 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 3 till 300 digits, right? Now as I have told you, the idea of Chinese remainder theorem is very clear. Just take the first term, which is any of the terms. You can take 69 upon this thing, or you can take 168 upon the common difference. At this point what I would say is that take 69 by 99, the divisor that was given to us initially. You realize that the dividend 69 is less than the divisor 99, so eventually my remainder is going to be 69 only. Why? Because this thing can be very well written as 99 into 0 plus 69. So this is my final remainder to the question, what happens when 131313 till 300 digit is divided by 99. So we have been able to establish the idea of Chinese remainder theorem. Now hold on, I'll give you a question for your practice, and the answer to that you can write to me in the comment section. And the answer and the question that I'm sharing with you is, this is your homework, 5769 dot dot dot, the same number 5769. I should write this once again, 5769 till 400 digits divided by 792, and you're supposed to tell me the remainder to this thing. This is your homework. I'll be waiting for your response in the comment section. Thank you.